Well, good evening, 510, 610 people. It's Dr. Keith Schubert again on our next video for part of my makeup series that's going on for while I'm away. And this time we're going to do a little talk on virtual memory and some security issues and things like that as it comes up. Now, first off, we should talk about what virtual memory is and why we have it. Different parts of virtual memory have been around in computers actually for a very long time, because essentially you want to be able to have your memory be movable, and it's a lot easier from a programming standpoint if memory looks like it's one big cohesive block, so that you don't have to, as individual programmers, move things in and out. This also creates a danger area. If individual programmers have direct access to anywhere on the disk as it's going on, you have access to whatever information is there. So what you would like to be able to do is to allow a programmer and any program that's out there to essentially see what looks like one contiguous block of memory that they can access and they can work in, but they can't see the other stuff. It's just completely invisible to them, unless it should be permitted to them through a safe outside area like the operating system. So from a security standpoint, we want to have this nice kind of segmented out pieces of data. And this is one of those ideas that comes in. Now, segmentation not only is used for this kind of general sense where we talk about there's different segments of memory, but there's also a scheme that goes on with this called segmentation. And so when we start talking about virtual memory, there's two basic ways that you can handle it. There is paging, which is one scheme, and the other one is segmentation. Each one has their own advantages and disadvantages. So for instance, let's say we have a chunk of memory that's out here, and we wanted to parcel this memory up for different programs and for different purposes that's going on. So our data is stored here, address is moving down. Now, one way I could do it is the idea of, if some particular process, maybe only needs a little bit of room here, exactly the space that they need. Something else then comes in and, whatever. So this is, first process that's out there. There's some second process and it requires a lot of space. And then maybe there's some third process and it requires just a little tiny bit of space. And maybe there's, a fourth one that comes in and it requires a nice little chunk, and a fifth one comes in and it requires a little chunk here, right? And then let's say there's a sixth one that comes up, and it does not fit in this remaining space that's on here. And now maybe we go in and we come back and we close out a few processes. Maybe 6 requires, let's say, like this much space to go in. This is what 6 needs, and we need a space that size. And I close out, 5, it's not so important to me. And I close out 3, as it goes on. And at this point, if you added up the little chunks here, I actually have enough between this space, and this space. But it doesn't fit in. This space where you give people exactly the amount of space they want and kind of fit them in is called segmentation. Now, it's great in that internally you get exactly the amount of space you need. So you don't fragment memory inside, you get what you want. However, as processes close, they're in particular areas, and to those individual ones, I might not have enough memory to fit in. Now, straight segmentation like this isn't super popular. Paging is much more common, although aspects of segmentation do get pulled into it. But this is a common one. This is called external fragmentation, because your memory has now been fragmented on an external scale. Now, an alternate way that I could do this is to take memory and break it up into nice even-sized blocks. So now when you're fitting things into a puzzle, so to speak, if every one of these is exactly the same size, we call that a page. So think of this like a book that's going on. A fairly typical size that goes in is a 4 kilobyte page. Now, if I've got a 4 kilobyte page, and let's say for the sake of argument, just to keep things, nice and reasonable, let's say I've got 8 gigabytes of memory that I'm trying to divide up. How many pages fit within that RAM that's going on? Right, well, what I've got here is, 2 million, right? Because I just take 4K goes into 8 gig, and it leaves 2 million. So I've got 2 million and that's 2 million in the binary. That's, this is 2 to the 20th and 2. So this is technically 2 to the 21st, 4 kilobyte pages. This is a note on there. But 2 to the 21st is really darn close to 2 million. Close enough that it's worth going on there. If you have to actually calculate it, it is worth noting that it's actually 2 meg going on, because this is 2 to the 33 as it goes on in. Right, this right here is K is 2 to the 10th and 4 is 2 to the 2nd, so this is 2 to the 12th. Now, as a note, 4 kilobyte pages is standard x86 type program, because what they did is you had 32-bit addressing, and they just broke it up. You had 12 bits that were your offset inside the page, and then you had 2 different 10-bit addresses to get the particular page you're on in the page space within memory that you were at. Sometimes people just kind of lump that together as a 20-bit reference to where the page is. So 4 kilobyte pages are pretty common because it kind of got originally imposed from the Intel system. But it's actually a pretty good size as things are going on. The nice thing is, if everything's up that, right, I can get a whole bunch of them. And now it's kind of like having a puzzle where every piece is the same exact size. It's very easy to fit things in. Right, now at this point, since everything fits in nicely, it's easy for me as, an operating system or something to fit whatever programs you want. I'm not going to end up with some spot that's a little bit too small because everything's the same size. Now you might need multiple of these, no worries. I can even make those look contiguous if I need. So there's plenty enough nice things going on here with paging, which makes it fairly easy to do stuff with. Now at this point you go, wow, there's no of that external fragmentation problem. The problem is I have to take everything in 4 kilobyte blocks. Even if all I need is 1 bit for a bool beyond where I need, I'll have to get another whole page. Right? So I might have internally a huge amount of wasted space. Right? So externally there's no problems. Everything fits in perfectly. Right? That was not the case with segmentation. Segmentation had external fragmentation, could cause all kinds of problems. Now what we have going on here is externally everything's perfect, but internally I might only be using a tiny bit, or I might use a first page perfectly and a little tiny bit of the second page. And a little tiny bit into the second page, I got this whole bunch that's wasted in here. Oh well, that's called internal fragmentation. Now I've got a bunch of wasted space that's going on, and I can't use it. So therefore there is waste going on again. The question is, where do you want the waste? As I've mentioned many times before, life is a trade-off. You pick where your efficiencies are, you pick where your waste is, and sorry about it, just live with it. Right? You pick the one that fits you best. Now, we've talked and mentioned a few things. I mentioned this is nice for security. We see a little bit nice stuff here in paging, and it's reasonable. You can calculate addresses and page sizes and whatever else. But let's talk a little bit more about some of the nice things that this buys us, because there's a lot of important things that go on security-wise if they're properly used. Now, the nice thing about this is if the operating system does its job and it allocates to me, let's say it allocates to my process, the 2 pages I ask for my stuff. Right? And all my stuff, for the sake of argument, fits within those 2 pages. That's all I can see. If it does it correctly, it allocates my memory to me, and I cannot see the rest of this. All of my loads and stores are to RAM. The only way I can access the hard disk is the hard disk is on a page that's not inside RAM, it's on the physical disk. So when I try to access that address, because the physical disk is added right on here, I try to access that address as part of my overall memory scheme, it will get pulled into memory. But if I don't have access to it, I can't get there. I have to go through the OS, and the OS can check, do I have the right to get to that spot? So you can now actually impose very nice security systems on here, right? With each page, we can actually put security information, who can actually own these and everything else. In general, what we have is we have two different users for our particular page. We have the super user, which is the system, and then we have the regular user, which is the process that's going on. You might think, well, that's not super safe. But it's a lot more safe than you think, because what you get is, I'm either the process that is running, or I am the super user. And any process that's not running is not me. They can't access my memory. They're not the user, they're not the super user of what's running. When they come up, all they can see is their own memory. To access somebody else's memory, they'd have to be the super user. So it actually provides a lot of security there as it goes, done correctly. So that's one of the reasons that we really like this as it goes on, is it provides us with that security when it is handled. Unfortunately, a lot of systems do allow you to go past the edges. This is where you should hit segmentation faults and things like that. You've gone outside your segment and you don't have permission. Now, those type of areas should require you to have to invoke to system calls or whatever else that's going on. And hopefully those things have been implemented properly on all of your systems. Sadly, sometimes it does not happen, but many times it does. But that's the basic idea of what it does. It gives me a nice little block, and then when my thread is not being run, my pages can either be left in memory and nobody else can access them because they don't have the right permissions, or you could swap them out to disk. Now, anytime you go to disk, you're paying a lot of cost because disk is, relatively speaking, slow in a latency sense. And latency is what matters for the execution of instructions. Bandwidth, I can pull those pages in, once I pay the latency costs, I can pull the data in fairly quickly. But there is a huge cost that goes on in just that initial latency. It's, 20 million plus cycles, somewhere in that zone. So going out to hard disk is pretty expensive in that sense. Now, the next thing that we can do up is a statement, right? We said the operating system has the ability to pull these things in. But what we can actually do once we have virtual memory systems is we can actually treat the operating system just like any other process that's out there. So I can actually have virtual machines. Now I can get a virtual machine simulates a piece of hardware, and we just think, oh, that's a great thing. I can simulate, on a Windows machine, I can simulate a Linux, or vice versa. I can simulate a Mac or whatever else is going on, or I can have a Java virtual machine. But think about this: that virtual machine can be running operating systems, and that operating system can see a different instruction set architecture because the software can simulate, albeit with some delays and whatever. The performance is going to be less than straight hardware execution, but it allows you to then imitate any other hardware ISA that you want to do. So there's a delay, but you could actually even have multiple operating systems that are looking like they're running on various different ISAs that are out there. That's a nice feature to be able to run. On top of that, each of those operating systems sees its own little block of memory, and it thinks it owns everything. And what's really handling that, so it sees this, it doesn't realize these other resources here. So I can have OS 1 running over here, and I can have some other operating system, I shouldn't call it OS 2, I'll get in trouble with IBM, maybe I'll call it, OS A, yeah, that's running in some other area. And they're completely independent of each other. So we can have multiple ones right here. The one that then really connects between them is sometimes called the hypervisor. Right? It's like a supervisor next level up. So it's not just supervisor, it's hypervisor. You'll sometimes hear that term bandied around. But it's also called the virtual machine monitor, or VMM. And that allows you to switch between the different virtual machines running operating systems. And this is a nice, safe way to be able to handle things, right? I can launch, if I don't want some virus from the internet, and people hide things everywhere nowadays, you can even be diligent and stick to safe sites and whatever else, and it's, people come banging on your door. Well, you can actually have an operating system that's kind of a sacrificial dummy operating system that has nothing in it, that you stick running on a virtual machine inside your main operating system. Now that thing, they can hack and tear that one apart, but they can't get into the rest of your computer, right? They can destroy your whatever you got in there. That's, you usually just would put in a web browser or something like that, and, then just have your operating system right inside there. They can tear into it, but they can't get outside of it because, your virtual machine monitor won't let them out. So it gives complete security between the different partitions. They can't access your data, and you decide you want to get rid of that operating system. It's been compromised. You just delete that little partition it was in, make a new partition again, reinstall, and you're back up and running from an image that was safe just before then. So it gives a nice way that you can protect yourself from a lot of these internet dangers that are out there, if you're willing to spend the time to do it. These are some of the things that virtual machine monitors, various virtual machine areas, and virtual memory buy you as you're going through. So it's got a lot of great features that are extremely helpful. You do pay a little bit of a performance cost going to a virtual machine and dealing with some of the virtual memory areas, but the simplicity and the security that it pays you back more than offsets this. Now, to be able to handle this, right? So this is some of the reasons why we might want to do this, and kind of some general structures in them. We talked a little bit about some of the addressing schemes, right? The 4 kilobyte pages allow you to get them. We're going to do the same thing that I kind of just mentioned. We're going to lump them together. We've got our 12-bit offset. When you locate a page, the offset, right? Here's my page that's 4 kilobytes. When I'm trying to find a particular variable some point in here, there is an offset. This page being 4 kilobytes means it needs 12 bits to offset it. So I get a 12-bit address from the initial point, tells me what's going on here, which means this page is 20 bits of X, right? X, X, 20 bits, which tells me where is the page. And then the page itself, its first reference area is all zeros. And then anything inside it is filling in this offset, right? So, maybe 0, 1, 0, blah, 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 right? So now you get non-zero entries. This portion here is the offset, and it tells me how to find that address. Now with virtual memory, what I'm doing is I've got my overarching, what looks like a gigantic logical memory, and then I've got the physical memory that's going on. That's my RAM and my hard disk and whatever else. And I make it look like one gigantic piece that's going on, and I just load whatever's being actively used inside my RAM portion, and I can swap things out into my hard drive. Now, I can move it around on this side because what's happening here, any particular page, your program references it as if they are exactly in the order. My first page, my second page, my third page, my fourth page, whatever else is going on. These are my pages, and the first page could be stored over here on the hard disk, and the second page could be currently residing inside memory, and maybe the third page is residing in some non-contiguous block inside memory, right? as it's going on, somebody just has to translate. Your program deals with this set of addresses that looks nice and clean and contiguous. But really what it's trying to do is access RAM or hard disk or whatever. Somebody else is doing the translating. That's what's going on inside the page table. And what the page table does is it takes that address and it's got the offset and it's got its page number. Right? That's what's coming in here. What looks like logical areas. This comes in trying to reference something, and then you've got to find it. But this is not referencing where it actually is in the system. It's referencing this logical. So now we need some system that's going to take this part, the page number, and it's going to look it up inside a table. And then inside that table, it's going to have the actual page number, right? This is our physical one. And it's got some tag bits, which tells me stuff about user and permissions and everything else. But it takes this part of the page number and it takes the offset and it creates an actual physical number, which is then used by the physical system to find out, is it in RAM or whatever else. So we have to do this conversion. This is done by the page table. Now, in general, this page table is actually stored inside memory. Now, this might start sounding like turtles all the way down, right? That there's, I'm using memory to handle all these things, and then I'm storing the table inside memory. And you are right, there is a danger here. If the part of the page table that tells you where the rest of the page table ever gets cached out of RAM, then this process can't find the page table. If it can't find the page table, it can't find anything. And now you're in deep trouble. So there is a portion of this page table that absolutely must be kept inside RAM. We often call that being pinned. Right? So we just like you would say you pin something to the start menu, so too we have to pin certain things in RAM. Well, this table thing has to be true for every single program and everywhere in it, including the program that handles this. So that program has to make sure it always keeps the address to tell it where to find things. It has to keep that in RAM because that's where it can look. And then from then on, once it can do that, it can find the rest of it and load in what it needs. So there are some things like that that just have to stay in resident. These are usually OS tasks, which includes this. And basically the handling of virtual memory is by and large a task of the operating system. Now from the hardware side, which is really where we're concerned in this course, so a lot of this I push off and say this is your OS course's job, and I mention this as it goes on, but I'm not going to spend too much time because that's, you either get that in the basic OS course, which is 460, or the advanced one, which is 660. And I don't want to steal any of their thunder. That's, they do that quite nicely and in covering the material. What I want to do is talk about the areas in hardware that we have to do to support this. There's some of these elements of the page table are particularly commonly used by your program. Right? I mean, if partition 1 here has been stuck out on the hard disk, that's only because you really haven't used it. Because otherwise we're not going to pay that 20 million cycle penalty to pull it back in if you're going to do that every 5th instruction. So we pull into RAM everything you use somewhat commonly. The stuff that's not in there is stuff you haven't used in ages on this program. So, unless you actually get a system that's not doing a good job, we call this thrashing, where it pulls pages in and drops them back out and stuff like that. But that's a sign of a badly programmed or badly configured system. So if you are thrashing your disk as it's going on, paging in and out and things like that, then, it's a bad program where something is set up wrong, and you should certainly fix that. But, like I said, there's some of these that are fairly common. I don't even want to actually have to pull the OS up in its special process every time I do this. Because think about this. If every time I access RAM, I have to pull the operating system up, that means I have to do a system command, right? Which means I'm going to have to do, a call on this, and that call itself actually involves using a paging table to look it up, because whether it's an interrupt or however else you are handling this as it's going on, all of these use a vector table. That vector table is in memory, so that would involve me looking things up. So there's a lot of things. I might have to do several different calls to this paging table to be able to solve something. If I have to go through that, that would be prohibitively expensive. In a lot of those cases, I'd be even, when I'm doing system calls, I'm having to switch my run level, to go to a super user state and all kinds of other stuff that's going to be very expensive for me to go on. Don't want to have to do that every time I load a variable. You'll get horrible performance. So what we need to do is have something that's like cache for the commonly used ones that are out here. And you might think, hey, well, why not just use cache? Well, the problem is that cache would be in somebody else's segment. It'd be in the super user segment. So your program, couldn't get easy access to it. So again, we would still have that same problem. So what do? We need to build a cache for this table that can just do its job automatically. And what that is, it has to be able to do translation, but it's something that we ought to be able to just look aside and do it quickly. And it should have a cache, usually, highly associative, if not fully associative. It's going to be a fairly associative area. It's a very small cache, and it just contains the top several pages that are being used in, and it is a translation look-aside buffer. And so we build this special cache, it'll reference into it, and it will have just the common entries, but then we can grab those out and handle this. And this will work automatically for you inside the hardware, and this has to be supported on the chip so that you can go out to cache and access everything that's out here nicely. And the TLB will look and say, do I have it? If you do, then you're in great shape. It's been used recently. It's going to be in RAM, all kinds of nice stuff. So at that point, things go ahead. It's doing this quickly on the side. Essentially, you don't really incur any penalty. And it just converts it, sends it to the cache, and you're done. Now, if it is not inside the TLB, now you're going to have to call the OS and get the whole process going. That's expensive, but there's a chance you could be going to the hard disk. That's really expensive. So you might as well do it right at that point and call up the table, and away you go. So the building of this TLB as an intersection to handle this translation from what is this nice looking logical memory that your program is able to interact through virtual memory to what's actually physically out there. We try to use this very small little cache called the TLB to do that process. And that TLB is storing the portions of the larger page table, which you talk about heavily inside your operating systems course. So this is just kind of our way of doing it that keeps our performance up of being able to access cache and RAM with the correct address by just pulling that table from there. So, and then everything you've got from your operating system course, which gives you your security things, are handled nicely, and you've got your contiguous memory from your programming, so it's a simpler area. Make sure that things are handled well in those areas, and you have this wonderful way of pulling things in and out of RAM and hard disk. So if everything goes nice, we've got security and simplicity and speed. So this is kind of a hard to beat combination, but it relies on you having hardware speed ups like a TLB that's going in. So hopefully at this point you feel a little more comfortable about what's going on. You can read through the sections that are inside the book, and I will be back next week to help you guys with whatever problems we might have. Have a great evening. Bye.